Hi, everyone. It's great to see you at the Cosmo from home this year. My name is Yuhsin. So the organizers suggest me to talk about some cosmological probe of new physics, and which is such a broad subject. And there are definitely many things that people have been thinking about, and even you have been studying about. So I'm trying to limit the goal a little bit by focusing on the dark sector cosmology that people have been doing um, with some connections to the particle physics models that particle physicists have been thinking about for a long time. Okay, so more to find um, strengthen the motivations to study the dark sector cosmology. Okay, so let's start. Um, So I was trained as a particle physicist, and the reason why many of us got drawn to cosmology is because whatever new physics we have been thinking about, we know it should show up sometime in the early universe and somehow changes the behavior of the universe. Okay. Um, so which can start from like right after Big Bang, when the universe is still in the inflation phase. If there are some new physics shows up during inflation, cosmological particle production, or some additional field that has a different quantum fluctuation and generate some features, um, it can leave imprint on the primordial curvature perturbation, so we can see it on the CMB. So that's one possibility. Um, um, or if there are some physics that really just shows up at a late enough time that directly modifies CMB, modifies structural formation, or sometimes it can may destroy something in BBM, then we can also use the cosmological data to study that. Okay. And it's also equally motivated to imagine there are some new physics that happen in the scale in between because such a large scale, right? Between the BBN and all the way to the inflationary physics scale. So there can also be new physics there. Okay. Um, and I'm going to come back to those new physics on the scale. But the good thing of cosmology is that the universe is a great gravity detector, meaning that when I use it to study new physics, I can even looking for new physics that only have gravitational interaction to us. Okay, because whatever interesting dynamics happens in the hidden sector or secluded sector, depending on the words that you like to use, it can modify the gravity perturbation in the background and therefore imprint signals on the photon, baryon distributions. So we have all the different ways to look for such signals, even gravitationally. Okay, so that's awesome. So this relates to the modified curvature perturbation or modify the transfer function for the CMB and large scale structure physics and things like that. So that's great. But as I mentioned, how about all this new physics that shows up post-inflationary, but before BBM? This includes some highly motivated new physics scale that is around electroweak scale in the Snell model, all the way up to order 10 to 100 TeV scale. That many of those are also covered by together by the collider experiments, or maybe the futuristic collider experiments that people have been building up to study new physics. Okay, so within this region, what can cosmology do? Okay, we know it's highly non-trivial because whatever new physics that may show up here, they address various of particle physics puzzles that people have been care about. The effect of those physics, the signals may already be washed out when the universe was deep in the thermal equilibrium phase. Okay, so it's really highly non-trivial to imagine there will be a signal here got left over so we can still see directly. Okay, so it's such a pity because we do have lots of motivations to expect new physics will show up somewhere in this scale. So now this is the main question we want to ask, and I'm going to give you some examples on this, which is that can we come up some motivation, or are there motivated models or scenarios that will connect the physics at this high energy scale, but not as high as inflation, but can be studied with cosmological data? Okay. Okay, so I'm going to show you the dark secret cosmology that many of us are studying is not just an interesting case study to showcase how powerful the cosmological data is, but it can actually be useful for some of the long-standing puzzles in particle physics. Okay. First example I will be talking about is the neutrino cosmology. And I will tell you how can that be related to the origin of the small neutrino masses, okay, which is a puzzle, right? Which is kind of weird because if you look at the particle mass spectrum in the Snell model, the mass of all the elementary particles in the Snell model, even for the lightest quarks, it ranges from MeV scale to order 10 GeV scale, and then there's a Higgs and W and Z bosons around 100 GeV scale. So it's roughly all around this energy scale. Every 1 decade in terms of energy scale, we see some particles around. But somehow, right below the MeV scale, there's really nothing, and go all the way to be the sub-EV scale, 0.1 EV or milli-EV mass, where from the neutrino oscillation experiments, we know that's roughly the scale of neutrino mass that shows up with such a big hierarchy comparing to all the other elementary particles. And it's not zero, okay? If the neutrino mass is zero, that's fine. There's probably some symmetry why neutrino cannot get mass, but we know it's non-zero. So what can explain this hierarchy between the masses of these different particles? There are several examples that the people discuss about, so there's no way I can go through all of those. But there's one example that is very relevant to the cosmological study, is the following, okay? So the idea of why neutrinos are so much lighter is because that they get a mass from a different symmetry breaking comparing to the Snell model, other Snell model particles. As we know, in Snell model particle, the way the quarks get mass and the charged leptons and the W and Z bosons get a mass is by coupling through Higgs. Okay, and the Higgs has a spontaneous symmetry breaking, so that sorts the mass of these elementary particles. Okay, so it can be that the neutrino, the reason why it's so light, is actually getting a mass from a different symmetry breaking comparing to all the other particles. So if you are a cosmologist and haven't thought too much about the particle physics, don't worry. I'm going to try to explain it in a way that there's a more focus on the big picture. Okay. So one possibility that has been discussed for a long time is not just one specific model from me. It's really there are lots of discussions already for a long time. Is that maybe this additional symmetry breaking that gives the neutrino mass can show up at a different energy scale, that's just called the F, and which got mediated to the Snell model neutrino through some heavy physics at the scale lambda. These are all energy scales. So that they're different from the other small amount of fermions or gauge bosons that they get a mass by directly coupling to Higgs. The neutrinos can only get their mass once there's other symmetry breaking happens from other field, and they couple to the neutrinos through some heavy mediator. Okay, so this is discussed in many of the early literatures. Just give you one specific example. Now, for example, you can imagine if there are some symmetry reasons that when I trying to write down the coupling between the Snell model lepton, including neutrino, to the Higgs, I can only write down the term with the two neutrinos that will source the neutrino mass to some other field and suppressed by some mediator scale. So that once this other field gets a symmetry breaking, so gets a VEF, that will give me effective mass term of the neutrino that go with some ratio of the new physics energy scales, and V is the Higgs VEF. So this is the simple idea. So by playing with a little bit of hierarchy between the F and the lambda, there is a chance I can explain the neutrino mass and say, why is it so much lighter? Okay. So far, these are just particle physics, right? So what's the connection to cosmology? The interesting thing about this kind of ideas, again, from many previous works, is that when I have a symmetry breaking that is going on, that source the neutrino mass, I usually have something called the Goldstone boson particle, which is a massless scalar particle that will show up to compensate the degrees of freedoms for changing the degree of freedoms from symmetry breaking. Okay. So what does this Goldstone boson, or usually people call it as a majoron, when we're trying to source the majoron mass using this mechanism? So what would it do is it can couple to neutrinos. So once you have a massless particle that can couple to different neutrino mass eigenstates, you can allow the heavier neutrino to decay into lighter neutrino and some massless particles. So this is the neutrino decay that doesn't produce a photon, so we don't get to see it directly. So it's an invisible neutrino decay. And then at least for the model that I just wrote down for you, just as an example, you can calculate what's the decay rate comparing to the Hubble expansion rate. Okay, or you can say this is comparison between the lifetime versus the age of the universe, and it can be comparable to each other. So to the age of the universe, if your new physics scale for the symmetry breaking is of order 100 TeV scale. So that's a scale I mentioned before that can have many new physics that shows up. Okay, so neutrinos can easily decay invisibly in this way, associated to this energy scale that generates neutrino mass. And it's actually very challenging to constrain or to probe the neutrino decay with such a long lifetime. Because all the long baseline neutrino experiments, the lifetime constraints are pretty weak. Okay, 10 to the minus 14 seconds, not even second. We produce supernova neutrinos far away, but those neutrinos are highly boosted. So ends up, if you translate to the lifetime constraint, it's also very weak. There are already bounds from the CMB by saying the neutrino needs to be free streaming because the neutrino decay and the inverse decay can make the neutrino to be interacting. And those bounds are usually correspond to the time scale of order 10 years. So which is still way shorter than the age of the universe lifetime. But interestingly, if we do think more carefully about the neutrinos that can decay while being non-relativistic, so meaning that really decays at a much later time, and think more carefully about the CMB and large-scale structure signatures of that, we do have a chance to constrain the neutrino lifetime all the way from the 10 billion years of the age of the universe. Okay? So why? So what's the signal? Okay. So one way to think about the effect of this invisible neutrino decay is that we reduce the amount of warm dark matter abundance that should exist in the lambda CDM model with neutrino mass. Okay. So here I plot a ratio of the dimensionless energy density contrast of the cold dark matter of the total dark matter with and without the existence of neutrino mass. Okay, so this is still a stable neutrino scenario. So neutrino is just stable warm dark matter. In this case, when I calculate the ratio of the energy density contrast as a function in redshift or time, what will happen is that the early time, when I compare the model without neutrino mass, the neutrino mass doesn't do anything because the early time neutrino is considered as massless. So this ratio will be 1. But once neutrinos start to be non-relativistic, their energy density becomes more important during the matter domination era, comparing to radiation because they got redshifted more slowly. But these are the matter density that doesn't cluster. So this is going to suppress the matter density perturbation. So I begin to see the suppression of the density perturbation comparing to massless neutrino scenarios. Unless the CC dominance, the structural formation stops, and then it got plateaued at a certain value. So this is the history of stable neutrino. Okay. So what if neutrino decays? Okay, and it's very simple. If neutrino decays, let's say for the blue curve, when a neutrino decay rate is compared to Hubble, so neutrino energy got converted into radiation energy, then this radiation energy for the ghost boson or like the very light neutrinos, they will just redshift away very quickly because they behave like a radiation. So that's why the amount of matter density that carries a small perturbation, that amount is less significant compared to the stable neutrino case. So as a result, the suppression of the density contrast becomes milder. So I actually get the enhancement of the perturbation in the end compared to the stable neutrino scenario. And depending on the lifetime, of course. Okay. So this is the idea. Okay. So with this, because this also imprints the signal through the CMB lensing, we can already use the existing data to say the bounds on the lifetime. But as you can imagine, this lifetime constraint will be mass dependent. Okay. So that if the lifetime of the neutrino is very long, so on this plot, the y-axis is the decay rate of the neutrino, and the age of the universe is the Hubble is like 100 kilometer per second per megaparsecond, so it's like here. So when this is 100, this is about the age of the universe lifetime, or the inverse of that, the decay rate. So when this is the case, you will get an upper bound. The color region is the excluded region. You will get an upper bound on the sum of the neutrino mass to be similar to the result from the Planck, because there we assume the neutrino are stable. So that's the bound you will get. However, if you start to consider the neutrino may have a even shorter lifetime, then you start to relax the constraint on the neutrino mass, meaning that you can have heavier neutrinos that decay at the earlier time, so they fake as a lighter neutrino. So this exclusion bounds give you the information that for a given mass of the neutrino, how early do they need to decay to satisfy the current constraint? And this is basically the current situation. For this Y region here, this doesn't mean that we don't have a bound. It's just that it will take more work to study the bound here because neutrino will have to decay while it's still semi-relativistic. So I just haven't got the chance to study this bond carefully. And I would be happy to chat more about this. Okay, so we cut the bonds to make sure the neutrino decays after becoming non-relativistic. So this is very interesting. We do have already some bound on neutrino mass and lifetime, but if the mass and lifetime are kind of relating to each other, the next question I want to ask then is that is there a way to break this degeneracy so that I can probe the neutrino mass and lifetime separately? Okay, so that's the next step. Okay. But before going that, I need to connect back to the particle physics puzzles, right? We say there are these ideas, we call it a majoron type of model that can explain why neutrino masses are so light. If you take the toy model that I gave you for the example that I write down the decay rate, one thing that you can do is to say if the neutrino, the true neutrino mass is of order 0.1 eV, okay, for the heavier guy. So the sum of the neutrino mass is about 0.2 eV. Then the existing bond already tells us that if this is the mass, then the neutrino need to decay for around this time, I mean, for this decay rate. And if you translate this to that the decay rate of the Hubble expression, this tells us that the symmetry breaking scale that gives the neutrino mass needs to be below the 100 TeV scale. Okay. It needs to be below is that otherwise the neutrino would decay too late, too slowly, because the decay rate is inverse proportional to the F. So this is very interesting. This tells us that if the neutrino mass is this value, then neutrino needs to decay fast enough to satisfy cosmological bond, and which already tells us what the new physics scale needs to be for sourcing the neutrino mass. So this is one concrete example how the late-time universe data can be used to constrain the physics at the extremely high energy scale with some motivation, which is the neutrino mass here. Okay, but come back to cosmology. Eventually, I want to determine neutrino mass and lifetime separately. Is there any chance to do so? Okay, so there may be a chance. Okay, the way to think about this evolution of the neutrino mass while decay is that first of all, if we think about the perturbation, the matter perturbation, here I do the matter perturbation square compared to the massless neutrino case. Okay, so I take a ratio to highlight the effect. If I have a stable neutrino with this 0.25 eV mass, it's ruled out, but this is just to illustrate the point, okay? Then again, at a high redshift, the neutrino mass doesn't show up, and the lower redshift, we got the separation of the power spectrum, as we said before, okay? But now if I turn on the neutrino decay, we get enhanced perturbation, as what we showed before, once the neutrino begin to decay, okay? But here is a degeneracy, right, we're talking about, because when I see the sky today, when I see the cosmological signatures at a certain redshift, I don't know if the power spectrum comes from a stable neutrino with this mass, or even heavier neutrino that got decayed, so that ends up having the same perturbation, which is this red curve here. If I only look at one redshift, I won't be able to tell the difference. So that's where the degeneracy comes from. However, if I get a chance to look for higher redshift measurement, do a higher redshift measurements, like maybe in near future, the Euclid can provide us a redshift measurement, maybe up to redshift equals 2, then I can begin to see the difference between these two assumptions of the models, so that I have a chance to break this degeneracy using the redshift dependent measurement. So with this, we just do a case study just to illustrate the point. So in this work, we assume there's some like models of neutrino for a given mass with some logarithmic, the given mass of the neutrino in terms of EV and some lifetime in the number of log 10 to show that really if you get to include the future Euclid measurements, at least from the projection that people did, and also with the existing constraints from the CMB and the BAO data, we do have a chance to shrink this contours for the sum of the mass and lifetime to be a closed contour. So this gives a hope that we may be using this to measure the mass and the lifetime independently. And then this will definitely give us a very valuable information about the neutrino interaction and possible link to those BSM models that are trying to explain neutrino masses. Okay, so that's the idea. Okay, so now this is neutrino, but this is not the only example that we can connect the high energy physics to the low energy cosmological data. Here, I want to discuss another examples from a very different motivations, which is the solutions to the Higgs hierarchy problem. Okay. So in this example, I'm going to show you how would the mirror sector cosmology or atomic dark matter cosmology that people have been doing for a long time can actually be related to solutions to the Higgs hierarchy problem for the electroweak scale physics. Okay. I know that people, especially the young physicists these days, have a very mixed feeling about the Higgs hierarchy problem, or in general, the naturalness problem, especially its ability to indicate there should be a new physics show up at a certain scale or not. I'm not going to get into this philosophical discussions about the naturalness of the universe. But one thing that I can say very clearly is that given the quantum field theory that we know, and also the 125 GeV Higgs that we see at the LHC, we don't know how to describe the quantum correction to the Higgs mass. Like all the other particles that we can do it, but for the Higgs, the only scalar particle we see in nature, we don't know what to do. Okay. The only thing that we can say is that, okay, maybe we are lucky, the very, very high energy physics, like a quantum gravity, will somehow work in a way that make everything to be fine and give us the Higgs mass we see. Okay, but that's basically just by saying let's give up until we know quantum field theory. Okay, but and I believe it's truly reasonable that if we believe that we don't need to rely on all the subtle things in the physics that we don't know at this point that show up in the extremely high energy scale, if there are some symmetry reasons or some other physics reasons that we know the Higgs mass is stabilized, the quantum corrections, it makes sense already around the Higgs physics scale, then for us, that's a much more satisfying solutions. So, and it's not we just give up everything. So that's why I still have a strong belief in thinking the Higgs hierarchy problem will indicate the new physics should show up around the electroweak scale. Okay, but then you will quickly say, sure, but we haven't seen anything, and that's exactly right. So that's the problem, right? So even though we have a strong motivation to think the new physics should be around the scale we have been probing at the LHC, but we haven't seen it. There are different ways to address this. And one of the idea that, again, have been discussed a long time is not from me, it's from this smart physicist here, is that maybe the reason why the Higgs mass, the quantum correction would make sense up to the energy scale we have been seeing so far, and we haven't seen the, we don't have to see the new physics for this, is that there is a mirror symmetry or some discrete symmetry that predict some Snell model-like particles that carry in the Snell model coupling and carrying the a mass has a tight relation to the Snell model particles that will also show up for the quantum correction of the Higgs mass and can cancel out whatever quadratic divergence in my radiative Higgs corrections. So that why the Higgs mass is still the pretty small value comparing to the Planck scale we have been looking at, or comparing to the 10 TeV scale we can probe so far. But while we haven't been able to see these new particles showing around, because they are mirror version of the particles, they have mirror photon and mirror gauge interactions. They just don't couple to us directly. So that's the reason why we haven't seen that. Okay, so that's the main idea. So this is called the twin Higgs model. Okay, so this is a nice idea to tell us what's going on and tell us don't worry if we haven't seen a new physics yet. Everything has been taken care of by these mirror particles. But then the question is that, what does that mean? Do we just say this is a solution and then we don't see it? We cannot check the idea. We don't have a signal to measure it. Is that the idea? Okay, so it's still not satisfying, right? So here comes the cosmology. The cosmology can actually be used to study this idea that the people come up for the particle physics reason. Okay, and the point is that because this twin Higgs model, with a strong motivation to address a Higgs hierarchy problem, actually predicts a more well-defined atomic dark matter setup. Okay, with a well-defined particle mass and couplings that we can use as the target for the cosmological study. Okay, so because of this mirror symmetry for solving the Higgs problem, in the low energy universe, we will have some mirror neutrinos as a free streaming radiation, some mirror photon as a scattering radiation in the beginning that scatter with the mirror hydrogen, mirror electron, and the mirror helium. Okay, and the mirror photon and these baryons will be scattering, interacting with each other in the early time. But at a certain point, the recombination will happen in the mirror sector. So they become the photon becomes free streaming radiation. And then the baryons can start to have structural formation, but with a much more delayed time scale. Okay, so this would be the content that would be fixed by the mirror sector. And there are some more details about the model parameter and stuff. And then if you're interested, I can tell you more about the details. Okay, but this setup of the mirror universe definitely provides us all kinds of different signals that people who studied dark sector cosmology have been thinking about. Okay, so here comes the cosmology side. First of all, the fact that when I have a fraction of the dark matter to be this mirror baryon that interact with the mirror photon will delay the structure formation in a non-trivial way, because it's like the Snell model baryon. Once the twin baryons just enters the horizon while the scattering to the twin photon is still efficient, it will have a acoustic oscillation process until the recombination happens in the twin sector. Then they will start to produce the structure, forming a structure. But this will already reduce the fraction of the dark matter that start to clump into structures So what ends up giving you a suppression. Okay. And moreover, for the different K modes that enters the horizon at a different time, depending on the size of the perturbation when the twin recombination process happens, this suppression will oscillate in the K space. Okay. So if I take this so-called dark acoustic oscillation process that has been studied again for a long time from various in various works, if I take my ratio of the dark matter power spectrum or the total dark matter power spectrum comparing to the cold dark matter scenario, at the small K mode, since my the dark acoustic oscillation already stops due to recombination, the ratio will be 1 for the low K modes. For the high enough scale, I will get suppression of matter power spectrum, but with these oscillation features here, they're relating to the sound speed of the dark photon in my dark acoustic oscillation process. So if we get to measure this overall suppression, the frequency of the dark acoustic oscillation and the starting point of the suppression starting from a given K mode, this is going to give us most of the information that I need to fix the behavior of this twin-Higgs model. Okay. And again, I will be happy to discuss more details about this. But we do have all these different features that we can use to study this model. Of course, I mean, many of you who are expert in the nonlinear corrections to the cosmological perturbation, you will say, hold on a second, okay? Because you will notice that when I show this plot, I say this is only from the linear order calculation. So it's not guaranteed that we will get to preserve these acoustic oscillation features once I include nonlinear correction. And that's exactly true. And that's definitely the thing that we should try to figure out what's the effect of this. So just for a very rough, and I would say still a bit crappy kind of nonlinear simulation, but it's enough to get some idea, is that if I take some of the twin-Higgs model examples, for details, you can check the numbers in our paper. You can see that once I start to run some gauge simulation, this is dark matter only simulation only. And I think even without doing a halo, this is only the dark matter simulation. You can already see that the power spectrum got smeared a lot at a very low redshift. But the chance that if we do go to a bit high redshift, like z equals 2, there's a chance there will still be some features got preserved, okay? And there may be some tools that we can use with the way that we use to study the Snell model BAO peaks, that we can use some of the halo informations and the informations of the velocity distribution to maybe reconstruct the linear perturbation. So that's the hope, okay? And here on the right-hand side, we just include these corrections to the two-point correlation function of the cosmic shear for dark energy survey year 3 data. Okay. So there are still works need to be done to be able to extract this information to better identify the model. And the higher redshift measurement will definitely be useful for this. Okay. And this is not the only signal for this atomic dark matter model in general, not even for just the mirror-twin-Higgs, but in general. We also have non-trivial models that show up in the CMB. So these are the two plots these two plots are showing you the ratio of the CMB temperature power spectrum and also the EE spectrum comparing to the model without acoustic oscillations, but including the delta and effective to get rid of that obvious corrections from the existence of the dark radiation. Okay? So you can see that even beyond simply adding additional radiation, there are these additional features in the TT and EE spectrum coming from the dark acoustic oscillations. Okay. Here, I don't have the details to talk about these oscillations. And for details, you can either see the discussion in my paper, or I will be happy to talk about this on the Slack channel. This non-trivial feature make the ratio to be different from 1, coming from basically from 2 places. One is that because of the dark acoustic oscillation, we damped the metric perturbation. So for the photon baryon, the Snell model photon baryon acoustic oscillations, we kind of shift that equilibrium point for the baryon photon perturbation oscillations, so that when I square that the perturbation, I will get a different enhancement and suppressions for the even and odd peaks. That's one of the thing that shows up on this plot. Another very interesting thing that gives me the difference is the behavior of interacting dark radiation that changes the CMB phase shift due to the different sound speed. And what is even more interesting is that this is not only for self-interacting dark radiation, this is the interacting dark radiation that scatter with the dark matter, with the mirror baryon in the background. So the mirror baryon provide additional drag force to the mirror radiation propagation, which will further enhance the effect of the CMB phase shift. So those physics, if you are interested on that, is discussed in these other works that I put out recently. I will again be very happy to chat about this. Okay. But with all this, the data we have today is already good enough in setting constraints to this the mirror-twin-Higgs model they used to address the Higgs hierarchy problem. So, for example, here I show you some plots that are used to constrain the model parameters. But just to fill in a little bit more details, when I show you the plot of this factor R hat here, R with a hat, this is a ratio of the mirror baryon compared to the total dark matter density, because it's very unlikely that all of our dark matter went through the dark acoustic oscillation process, because I think that's basically been ruled out. The bound is already, we already know the bound is definitely better than 10%, okay? So this is the fraction of dark matter that participate in the dark acoustic oscillation. The delta N hat is the total delta N effective from radiations in the mirror sector. And this V hat over V that I show you here is a ratio of the electroweak symmetry breaking in the twin sector versus the Snell model sector. So the V for us is about order 200 GeV, and V hat is the symmetry breaking scale in the mirror sector. The important thing is that the ratio of the V hat of a V indicates how well does this hierarchy problem solution does, okay? If this ratio is too large, then we again need additional tuning in the model to try to explain why the Higgs mass is so light. So the model doesn't do so well, okay? And a very, very rough idea, again, this is not a hard bound, it's just a very rough, give you a feeling of the bound, is that if this V hat over V is larger than 5, then the model start to have some kind of tuning again, so it doesn't work that well as designed, okay? So for this plot on the left, the Planck and the BAO data can already set some exclusion bounds for this mirror sector parameters, and already showing that the more preferred region should have the dark matter fraction to be below maybe definitely 10% level, and then with the V hat over V to be around here to make the model that works better. And the nice thing of this is that there are LHC constraints on some behavior of the Higgs decay can actually show sets a lower bound on this value. So together with LHC physics at the electroweak scale, we can already together put a very useful bond from this cosmological analysis. And then once I put the structural formation, large-scale structural formation constraint from the dark energy survey, I can also put another constraints on the ratio of the mirror baryon density. And then the model can actually give some interesting applications to addressing the S8 and H0 problems. I leave this for more details in the paper or for the discussion. I think it's time to conclude. Okay, to summarize, I hope that this talk gives you some idea or at least some examples that the dark sector cosmology is not only to showcase how powerful the cosmological data is, it actually addresses important questions in particle physics. Okay, so like the mirror-twin-Higgs model related to atomic dark matter cosmology, the majoron model addressing neutrino mass give you some interesting neutrino cosmology for neutrino decay. Okay, and therefore provide the different signals for the matter power spectrum or the evolution of the structure formation. Okay. There are more examples in this than the time that I have to explain. For example, there are other ideas called the unnaturalness scenarios trying to address a Higgs hierarchy problem. Will predict some minimum cosmology to be containing some multiple warm dark matter in the background. That will also provide some interesting signals. And for whomever is interested in this, please encourage you to talk to me. But the main idea is that we need both cosmologists and particle physicists working together to identify more of these examples for the dark sector cosmology that have some motivations, from strong motivations from a particle physics point of view. Because it's actually challenging. Most of the particle physicist models that people wrote down trying to address some issues, we probably won't be able to study them using cosmology because the energy scale is just so different. But here I already show you a few examples that may happen. Okay, so it should encourage us to try to identify more of these examples or more of the frameworks that we can put cosmology and laboratory experiments trying to study the new physics altogether. And thank you very much.